All right. We start chapter 4. Chapter 4 is, like I said, a switch from chapters 3 and everything before, where we used derivatives before. We're going to be using something different, chapters 4 and 5, which is going to end our course. In chapter 4, we discussed the second of the two main problems in calculus. The first main problem in calculus, where we spent the majority of our class, more than half of it, was, can you find the slope of a curve at a point? What was that? Derivative. The second question in calculus wasn't about the slope of a curve at a point. It was, can you find the area under a curve? Do you remember that question? I introduced it, I think, like the first day of real calculus. I said, can we do this? Given some sort of continuous function from A to B, can you find out what the area is between that curve and the x-axis, or basically the area under the curve, from here to here? And the answer is yeah. Yeah, and we actually have two ways to do it. I'm going to introduce to you what's called the rectangular method today. We'll deal much more with it in section 4.4, 4.3, and 4.4. They're kind of tied together on how to actually do this with the rectangular method, but I'm going to introduce it to you today. And then we'll talk about what's called the antiderivative method, which is a more concise way to do it. Are you ready for it? So I'm going to kind of go in a weird loop. I'm going to introduce this with the rectangular method. We'll talk about antiderivatives, then I'll use rectangular method to kind of prove what we just learned about antiderivatives. You follow me? So we have to wait till 4.3 to prove some of the stuff I'm talking about here today. I'm going to give you kind of an intuitive approach on it, though. Hopefully it makes sense for you. So first method, let's talk about the rectangular method and at least the idea behind it. So rectangle method. Rectangle method says, well, why don't you divide your interval into n, some number, n, equal subsections, equal as far as their width goes. Subsections, subintervals, whatever you want to call it. And create a rectangle in each subinterval, in each subsection. Hence where we get the term rectangle method, or rectangular method. So here's basically the idea. Let me redraw the picture for you. Let's say that I make this a little bit bigger too. Here's my graph. Here's my interval. The idea behind the rectangle method is, can you find the area under this curve the way it is? No, not really, because we don't have a formula for this, and even if we did, it doesn't have straight sides. And the only way we know how to take the area up till right now in geometry is if a figure has straight sides, right? Whether we can break it up into rectangles or triangles, because we know how to take the areas of those figures, or perfect circles, you know how to take the areas of those figures. This is not a regular shape that we know of. It's just some random function. In fact, I haven't even been specific. It could be any function. But the idea is, let's go ahead, let's break this up. We'll say, okay, we're going to split this up into however many parts we choose. Let's just assume those are equal widths. That's about right. And says if we have some sections here, what we're going to do in each section, since they have equal widths, so I'll tell you why we need equal widths later on in section 4.3, 4.4. But right now, let's just assume we have some equal widths. So our bases are all the same. Our rectangles, equal bases means they're easy to add together. That's basically it. So for each interval, subinterval, let's make a rectangle. Now there are several ways to do this. I'll show you one way. The problem is now, you got to determine how you're going to have the height of our rectangle. So one way to do this is to use what's called left endpoints, another way is to use right endpoints, and the third way is to use midpoints. And here's what that means. You go to the right endpoint of your interval. Here's my interval. I go to the right endpoint. I'd say I'm going to go to where that touches my figure. Does that make sense to you? A left endpoint would say I'm going to go up to where my left point touches my rectangle. A midpoint would say go to the middle, see where that touches the figure, and then make your rectangle. That would determine your height. So we have left endpoints, where that touches. Right endpoints, where that touches, or midpoints. Let me show you the midpoints, and here's how you do it. You go, okay, from my midpoint, I'd go up here where it touches that f of x, wherever my function is. That's where I cut it off, and that makes my rectangle. Does that make sense to you? Why do that? Well, it's actually not going to matter when we finish 4.4. We'll talk about what's called the definite integral. It doesn't matter whether you use left, right, or center. But for us, if we are always using one endpoint, sometimes we can systematically underestimate the area, and that would be a problem for us. Then this one would go, okay, let's go up. Where that touches, I'll draw the top of my rectangle, finish it off. And you would do this for every interval that you have. How many people feel okay about the idea here? The idea of drawing rectangles there. Do you see where the midpoints come into play here? The midpoint gives us the height of our rectangle. That's going to be useful when we get down to 4.3 and 4.4. Very useful. Now, how would I find the area of this figure? The approximation of this area. What would I do with this? If we know the area of a rectangle, which we do, right? A rectangle is just a geometrical figure. If I can find this area, and this area, and this area, and this, if I can find all the areas of all my rectangles, all I have to do is add them together, and I'm going to get at least an approximation of the area of my figure. You follow me? Now, is it going to be exact? Well, you can tell it's not. I mean, sometimes I've overestimated, sometimes I've left out some area. Sometimes it's about right, but sometimes, and I don't know whether I'm perfect or not. So I'm not going to be exactly right. It'd be a miracle if it was exactly right. It's not going to be a miracle. This isn't Harry Potter mathematics, so magic doesn't happen in math sometimes. But anyway, that's another topic, I suppose. It's not going to be exact. It's going to be an approximation. Now the question is, how can I make this better?
Taking a definite number of.
So would you agree that the more rectangles I have, the better approximation this will be? So, I mean, here I had 1, 2, 3, 4, 5, I had 6 rectangles. If I had 100 rectangles for the same width, 100 rectangles mashed up in there, I'm going to underestimate by a less margin, lesser of a margin, right? So the more rectangles I have, the better approximation becomes. So as the number of rectangles n goes to infinity, or as the space between the rectangles goes to 0, right? Does that make sense? If as a space, as this goes really, really close to 0, that's the idea of a limit. As that goes to 0, then I have a very, very good approximation. In fact, it's so good that it's exact. So the idea here is cut your region into rectangles. Every rectangle, you're going to take the area of that. Add all the rectangles together, and you're going to get a good approximation of your figure. How do I make it better? You let the number of rectangles go to infinity. The way you do that is let the space between them go to 0. For a better approximation, make the space between each interval Notice that in this context, the space between each interval, that's the width of a rectangle. Approach 0.